Hi there, how are you all doing? I hope you are studying about the metathesis reaction. Today we will mainly discuss on the Fischer carbons, their synthesis and their reactivity pattern, and if then time permits we will try to discuss the cyclopropanation reactions. Now let me quickly do one transformation on the Fischer carbon or the ring closing metathesis that we were discussing in the last class. What we have seen in the last class is the terminal olefin put together to make an internal olefin, or two alkyne can be even put together to make an internal alkyne. What if instead of two terminal olefin you have one olefin and one keto? Can you do the ring closing metathesis on the olefin and keto containing molecule? The answer is yes, you can do that. Let us look at one of those examples. Now, this is the olefin metathesis you are familiar with. The catalytic metal carbene is reacted with diolefin to give you a larger ring containing olefin compound. Now, what we have over here is a terminal olefin and a ketone, and in these cases once again metal carbene, but it has to be a stoichiometric version in this case, can give you the same product, and without much problem of course, you are going to get a metal oxide in the process. The intermediate that is involved in these cases are the one, as you can correctly predict, this olefin reacted faster to incorporate the metal into the substrate. Subsequently, this is 2 plus 2 and erythro 2 plus 2. 2 plus 2 retro 2 plus 2 gives this one, once again 2 plus 2 and retro 2 plus 2 would give you the metal oxide as the intermediate. Now, the next topic that we would like to move on is the Fischer carbene. You have seen the example of Fischer carbene. We will discuss in brief the structure and bonding and their synthesis. Mostly we will be discussing the reactivity pattern of the Fischer carbene. Now, Fischer carbenes are also widely used, just like your Fischer carbene. Fischer carbene are widely also used in synthetic chemistry. In lot of cases it is used when traditional chemistry cannot have any solution and you desperately need that compound. So, let us look at the Fischer carbene and its reactivity pattern. So, Fischer carbene. Now, Fischer carbenes are the one where you have a ligand metal and X R, this is the carbene center. M, this M is most often, not always, but most often it is a group 6 metal. X, this X over here is usually alkoxide, Nr2, Sr, etc. Of course, L can be often CO, not necessarily always, but it is often CO. If you look at the metal electronic structure, of course, there is a d orbital on the metal, which is a filled d orbital, Now, it can bind or interact with the carbene. So, this is the lone pair. Now, X and R is there on the carbene center. Now, on the carbon is having this empty C2p orbital. This is empty C2p orbital. Overall, then you have the donation from this lone pair of carbene, and the filled d orbital can gives electron to the empty C2p orbital. Okay. That is what the interesting part, you have a carbene 2 electron given into the metal orbitals, and metal d orbitals are interacting with the empty C2p orbital. Now, let us look at the synthesis of this carbene. Synthesis of the carbene is quite interesting and straightforward, I would say. Let us say you have a metal carbonyl hexacarbonyl species. This metal, as you were saying, it could be chromium, molybdenum, tungsten and so on. You can react with organolithium reagent. We have discussed this briefly over the beginning part, and from there on you can have this intermediate where this is a resonating structure between these two species, and from which you can put an electrophile. So, basically this is an SN2 reaction from where you can get your product, that is the Fischer carbene. So, this is the Fischer carbene that you are looking at. The most important part of this Fischer carbene synthesis is, it is unlike other organometallic intermediate species synthesis where you have to take a lot of precaution. Here actually these final compound are chromatographable. You can run a column on it. These are air stable even, okay. That is great from organometallic perspective. If you can isolate, purify and react it without any problem, that is going to be very, very interesting. So, the characteristic of these species, these organometallic intermediate are, these are chromatographable, air stable, of course, that is very, very interesting properties, and most importantly they are also thermally stable. Therefore, you do not have to worry about the reactivity pattern. Now, the good part of the Fischer carbene is they are equivalent to your carbonyl. Now, in a moment we would like to discuss how can you compare the Fischer carbene with ester and amide. Both ester and amide has a ketone unit CO, right. Now, how does it compare in reactivity pattern with respect to these ester and amide? That is the one we would like to discuss. What is the bond rotation energy between carbon and A or carbon and B unit? That is what we would like to discuss. So, this Fischer carbene as carbonyl equivalent, we have seen they can be quite interesting in this aspect, and they can be very, very beneficial while we are interested in a desired transformation. Fischer carbene as carbonyl equivalent. The first thing that comes to mind is, let us try to put the lone pair, that is the integral part. Okay. Now, you can write it down like M minus, and this is your plus. This is what the characteristic of the Fischer carbene. This carbon center is a cationic in nature or positive, and the one that you would like to draw further is the one where you have a double bond character between this carbon center and this A or XR in this species, right. Now, this is a double bond character, that means this is more of a in between, it is going to be in between a double bond and a single bond. Now, how strong are these bonds compared to esters? That is where we are interested. So, this metal center, as it turned out, this is same as for M equals when you want to put it as oxo, that means ester or amide. Now, we will compare, let us say we put it A double bond XR, A where it could be oxygen or metal, this is we are trying to compare with ester and R, and we will try to see the rotational barrier. The unit we are following is kcal per mole. If you have A as oxygen, and then X, this X equals O, that means it is a ester we are talking about, RCOOR. The rotational barrier is nearly 12 kcal per mole for this rotation we are talking. Now, X equals when NR or X equals N, then we are looking at 18 kcal per mole. If this is CrCO5, that means a Fischer carbene now we are dealing with here. Now, this rotational barrier for Fischer carbene, this Cx barrier is 14, okay. And if it is an Nr, then the Fischer carbene will have rotational barrier greater than 25 kcal per mole. So, this is very interesting, right. What you see therefore then, compared to ester and amide, normal ester and normal amide, your Fischer carbene, this carbon heteroatom bond rotation barrier is even higher. That means it has a better double bond character. Indirectly it says that the, let us say for example, this one is chromium pentacarbonyl, when your X equals chromium pentacarbonyl as opposed to O or oxygen for ester and amide, the rotational barrier is higher. That means it is much more electronegative. Chromium CO5 is much more electronegative compared to oxygen. That is a very interesting information qualitatively and quantitatively as well, because then we can compare and contrast the reactivity pattern of these Fischer carbene with that of the known ester and amides. Let us look at that, how to compare the reactivity between these two species. What we have then, chromium pentacarbonyl is much more electronegative than oxygen in electronegativity, right. That is an interesting phenomenon. What we can then try to do is the interconversion, right. We know that ester can be one ester, transesterification is a famous phenomenon. We can we convert one Fischer carbene into another Fischer carbene, much similar to what transesterification does. So, interconversions of Fischer carbene. Now, if you start with this chromium pentacarbonyl species and react it with another alcohol, for example, tert-butanol, okay, of course, this is going to be a reversible reaction. What you can get is the tert-butyl oxide or tert-butanol replacing methanol to give you that. Of course, since it is tert-butanol, you cannot do SN2 reaction, it has to be the one where you see the reactivity pattern similar to the one we have with amine as well. So, you can interconvert or you can exchange alkoxide with amine unit or alcohol with an amine counterpart, right. Now, that's having said that, then that sets up the right platform to do a number of interconversion. That tells you that if you have one Fischer carbene, from there on you can synthesize plenty of other Fischer carbene just by simply exchanging the different alcohol or different other amine. That means, of course, you have seen they are moisture stable or air stable, they are air stable, they are thermally stable, and of course, they are also chromatographable. That means, synthesis of these Fischer carbene becomes much easier, and without problem we can synthesize a variety of them. Now, one reaction that really comes quickly to mind is the Diels-Alder reaction of ester. because it is a diene-dienophile reaction. Your dienophile has to be electron withdrawing in nature, and that is how the Diels-Alder reaction goes. Now, how does it compare? What do you expect from a Fischer carbene? Can it participate in the Diels-Alder reaction? Of course, let's try to figure that out. The Diels-Alder reaction that we would like to do with these Fischer carbenes. Diels-Alder reaction, as we know, we can do with ene and ine. So, diene and dienophile. So, if this is your butene, if you are taking diene, and usually we are familiar with an ester over there, let us say for OMe. If you want to do this reaction at room temperature, well, you are in for trouble. This reaction, when even it is X equals O, this reaction does work, but as it turned out, it is little bit longer. Okay, how long is it? Of course, you have other isomer as well. If X equals oxygen, okay, and if X equal oxygen with a Lewis acid such as LCl3, and if X equals CrCO5, what would be the time frame that we are looking at? Well, that is a very interesting one. That is how perhaps PhD students are there for, to figure it out how easy or difficult these reactions are. If you are interested in doing this Diels-Alder reaction with an ester, for example, the dienophile, if X equals oxygen, can you imagine how long it takes? It takes 7 months. I do not know how did they do it, perhaps they set it and then waited for 7 months. I hope they have controlled it nicely, but overall what we know about this reaction is it takes 7 months to get even 50%, 54% yield, to be precise, for this dienophile and diene to react to gives the Diels-Alder reaction. Now, that is quite interesting, 7 months it takes. But when you are interested in putting some Lewis acid, that means you are making the dienophile much more reactive, then the reaction is done in days. That is very promising. But can you imagine when you take this X equals CrCO5, chromium pentacarbonyl, that means a Fischer carbene, well, that gives the reaction in hours. That tells a lot about the utility of this Fischer carbene reaction, how reactive they are compared to your traditional organic reagent. Okay, let us look at the yield of this reaction. This takes 7 months, give 54% yield. This takes nearly nearly days, I guess, days. It gives 95% yield. If this takes 3 hours, it gives 92%. Now, this tells you that these chromium pentacarbonyl species, they are the one acting more like a activated ester activated with a Lewis acid. Okay. Of course, that because chromium pentacarbonyl is much more electronegative compared to your oxygen atom. So, the ester oxygen or this Fischer carbene oxygen, Fischer carbene, this chromium pentacarbonyl can be compared directly and can be accelerating the reaction quite efficiently as one would expect. Now, that is a very interesting reactivity pattern comparison. As you have seen, chromium pentacarbonyl or the Fischer carbonyl can make the reaction very fast compared to your traditional Diels-Alder reaction, where dienophile is used as ester as compared to your Fischer carbene reaction. Now, let us try to compare a little bit more and try to see how they compare with the enolate chemistry, because all we are trying to compare is how the ester reacts and how the Fischer carbene react. then the enolate chemistry we should be able to comment on that. We should be able to comment their reactivity pattern and how efficient they are in this business. So, enolate chemistry, what we have traditional enolate, let us say if you want to compare this ester with chromium pentacarbonyl, this reagent that we get from the Fischer carbon. Now, as you know, lower the pK value, higher the acidity, where the pKa of this one versus that one. If this is nearly 25, what it is found is nearly 8. That is again very, very exciting. If you have an amide, now of course, acidity of this pKa or acidity of this is nearly 30, pKa is 30. If you have the chromium equivalent for the same thing, okay, now you have with this chromium reagent you have quite acidic CH, this CH is nearly 20. So, this tells you that this is directly comparable, the enolate chemistry or pKa value you can have is quite low. pKa low means it is a better acidic, much more acidic. This reagent or this part when you have this CH3 attached with a chromium pentacarbonyl, that is much more acidic compared to when the CH3 is a part of an ester. That means, if it is more acidic, therefore, what you can think of subsequently is doing the aldol chemistry. As you know, very familiar with the aldol chemistry. How aldol chemistry would be? Well, I would say it is going to be very, very reactive, and it is going to be very, very active partner in the aldol chemistry, right. Let us look at one of the aldol reagent or aldol chemistry with this Fischer carbon reagent, and we should be able to demonstrate the efficiency of such reaction. The chromium pentacarbonyl reagent we have, and then it is reacting with methyl counterpart. Now, this is the one which we have seen the acidity is quite good, and if you have N-Bewley at even minus 70-80 degrees C and you are interested in reacting with an aldehyde, we are doing a aldol reaction. Let us write it down, aldol reaction we are trying to do, and we get the product quite efficiently in these cases, and what we get is the expected aldol product with a very high diastereoselectivity, that is done at minus 78 degree centigrade. We get greater than 10 to 1 diastereoselectivity, and we have nearly 94% yield. Okay. Now, so I think with that we would like to close on this reactivity pattern of the Fischer carbon. As you have seen, this is quite interesting. You can have a number of, or any example that you know with the aldol reaction, you can possibly think about Fischer reaction. Not possibly, definitely you can think about the Fischer reaction. Right? These are much more acidic, the methyl group or the partner that is associated with the Fischer carbon is much more acidic. Any aldol reaction that you can think of, you can do. You can do the interconversion of ester to amide, or the corresponding Fischer carbon to one Fischer carbon to another Fischer carbon, and so on. You can also have a very good Diels-Alder reaction, as you were saying, Diels-Alder aldol reaction. So, whatever reaction you can think of with ester, I think you can pretty much parallel those reactions with much more efficiency and shorter reaction time, perhaps in most often better yield and so on. And once again, these reagents are very, very user friendly, right. You can isolate it, purify it and chromatogram it, and it is air stable, and it is also thermally stable. So, therefore, you can pretty much deal it with as if like you are dealing with ester and aldehyde, right. Now, having said that, now next topic that we would like to discuss perhaps in the next class mainly is the cyclopropanation reaction. Now, cyclopropanation reaction maybe we will introduce a little for this class, and then we will try to close today's class with the beginning of some cyclopropanation reaction. Cyclopropanation reaction is a very interesting topic where olefin is converted into cyclopropane by using often as you see diazomethane chemistry, and there are various reagent or various catalysts that we use, most often the rhodium catalysts, or of course, you have seen the copper and palladium combinations and different other combination as nowadays has come up. Let us look at the cyclopropanation reaction briefly, and then we will close today's class. Okay. So, catalytic, we will discuss only the catalytic cyclopropanation reaction. So, we are interested in starting with an olefin. We want to react it with a carbene equivalent, carbene catalyst. Overall, what we would like to get a stereocenter, of course, this. So, the common catalyst that we found for these cases is the palladium one, that for diazomethane chemistry, rhodium 2 and copper iodide for ester, diazo-ester chemistry. So, this is in equilibrium with, you can see that nitro plus, and this is carbon minus COOR. Of course, you can think of this diazo reagent, diazomethane CH2N2 and diazoester and so on. Of course, palladium and rhodium are the two metal that is used. Rhodium is usually often used in conjunction with copper, but it is as if like metal carbene, metal double bond CH2. This is the chemistry that is used for cyclopropanation chemistry, right. And this is a quite powerful technique and can give you cyclopropane, which are found in a number of pharmaceuticals, and industrially it is very interesting reaction, this cyclopropanation. So, in the next class we will try to discuss the cyclopropanation reaction, their asymmetric version, and also we will try to discuss the application of this in drug molecule synthesis or pharmaceutical synthesis. Industrially it has been used, and it is quite an efficient reagent for doing the reaction in both in academia and in industrial setup. Well, till then you start reading more on the Fischer carbene and maybe some also on the cyclopropanation reaction. We will come back shortly with more information, more materials on the cyclopropanation chemistry. Okay, keep reading. Bye bye.